Okay, are there any questions from last time? No questions. Okay, so let's continue where we left off. Remember, we're talking still about signals. So we're going to talk about signals for the good part of the lecture today. And then we have to go and define what we call a system, right? Because this whole course is about analysis of how do signals travel through systems, right? So let's first look at some useful signals. In other words, these are the signals that we're going to be using all the time. They're going to appear in pretty much all the work that we're doing. The first one that we're going to talk about is the unit step function. Okay? Or switch on function. This is how this one is defined. U of t, we're going to use the symbol U of t, is defined as 1 whenever t is greater or equal to 0, and it's 0 when t is smaller than 0. Graphically, this is how this function looks like. Before 0 is 0, and at 0 we turn the switch on, and after that this function is 1. Okay? So, very simple function. Let's take a look at examples of its use. U of t use. First example I have is what we call rectangular pulse. This is a function, or rather signal, that looks like this. It is minus t over 2 to t over 2 t, and the notation we use here is t over capital T. This is the pulse that has a length or duration of capital T. It is centered at the origin. It starts at minus t over 2 and extends all the way to t over 2. The pulse p of t over capital T can be actually seen as u of t plus t over 2 minus u of t minus t over 2. In other words, this pulse can be seen as built out of the two step functions. One is the step function that starts at minus t over 2 and kind of goes like this. The other one is the step function that is negative, delayed, and it looks like this. So take the first one and the second one, add them together, you're going to get to this pulse that is centered at the origin and has a width of t. The importance of this pulse is very big. One of the things that kind of can give you a hint of what we'll be using this pulse for, one of its uses, is the fact that if I look at any arbitrary signal, f of t, then I can see this signal as being built out of pulses, right? Approximately being built out of pulses, right? This is k plus 1, k plus 2, and so on. And this is some delta t, right? So I can see this signal f of t being approximated with this f hat of t. F hat of t I can write as sum when k goes from minus infinity to plus infinity. And I can say this is f of k delta t plus f of k plus 1 delta t divided by 2, which is the value at this point in between these two ends of the interval. So that's the average value of the approximation in this interval. And then I can say this is u of t minus k delta t minus u of t minus k plus 1 delta t. Right? So that's one way how I can approximate the function. And as delta t goes to as delta t goes to 0, you can see that f of hat of t becomes closer to f of t. And we're going to be using this quite a bit, later on when we talk about how we make things discrete and digital, right? So one way to see the world or see these signals as they are built out of these square pulses that are coming one after the other, that are relatively narrow, and that has the amplitude that is equal to the value of the function at the midpoint of the interval. So this is how we use the u function. You can see we can use it to express quite a large class of signals. Pretty much we can approximate any kind of signal by using just the u function. The second one that is very important to us as well is what we call the unit impulse function. Or famous delta of t. Delta of t is also kind of a constructed function. It is defined, and there are three parts to its definition. So how do we define delta of t? First thing that we say is delta of t is equal to 0 for every t different than 0. Whenever is t different than 0, the delta of t has a value of 0. So it only has a value at one point, right? And that's point 0. At the point 0, however, delta of t, or delta of 0, is infinite, right? And third part of the definition is that integral under the curve, so for integral from 0 minus to 0 plus of delta of t dt is equal to 1. So this looks like a whole bunch of, very weird requirements. So let me first, let me just give you how we draw this function. We are kind of drawing it like this, delta of t, and this is 0. The height of this is irrelevant because it goes to infinity anyway, so I can never draw it to infinity, right? So this arrow here indicates that this function goes infinity in the height. Now the question is, well, how do you get to this function? What does it really mean? And the best way to explain this to yourself is to look at this iterative process of how one might be able to create a function that behaves this way. So how do you envision delta function? Well, we can start by looking at pulse. Let's start by square pulse that has a height of 1 and width of 1. Right, so this is pi of t over 1. Right, so that's a function that we easily envision. Right, that's a pulse that starts at -half, ends at 1/2, it has a height of 1. What's the area under the curve? What's the integral here? What's the area under the curve of this pulse? 1, right? It's 1 long, 1 high, 1 times 1 is 1. So let's now move to a second step where here's what I do with that pulse. I cut its length in half. So it goes from -1/4 to 1/4, but I increase its height to be 2. Right? So this is now pi over t over 0.5, 1/2, and then 2 times in front of it, right? So this is this pulse here. It is 0.5 wide, and it's too high. What is the area under the curve here?
1.
So let me put it here. Area is equal to 1. Area is equal to 1. Let me do one more time. What I'm going to do here now is take this and cut it one more again. So this is from minus 1/8 to 1/8, but the height here is equal to 4. So this pulse here is 4 times pulse of t over 0.25. So what is the area here? Is equal to 1. So continue this process, continue it on. Every time I cut this in half, it becomes narrower and narrower, and then I double the height, so it becomes higher and higher. As in a limiting, if I allow this process to continue, in the limit I'm going to approach this function delta of t.
That means it's going to be constant.
What is constant? The area under the curve. So I'm growing this function infinitely high, infinitely narrow, but preserve the area under the curve. Here, I can actually draw that and explicitly kind of make it do that. But here I have to introduce that by definition. I have to say, what is delta? Delta satisfies this condition. I mean, there can be another process where I start with a 2 here that would satisfy these 2, but the area under the curve would be 2, right? That's yet another impulse, but it's not the one I'm defining. I'm defining the one that's a special that has these 2 properties, but also the third property that area under the curve is equal to 1. Now, this delta function has some properties. We're going to actually highlight only one of them at this point, but we're going to encounter this function very, very often. And I'm going to introduce other of its properties later when it's more appropriate. Here, I just want to introduce one property that's called shifting property of the delta function. And one reason why I want to introduce it is to show you how you actually do some of the math with this function. And it's really kind of important to us because it simplifies a lot of math. It is very convenient to do math with it, so we kind of constructed it to help us in presenting some of the properties of the linear systems. So one of the properties is what is called shifting property of delta of t. And this property says this: if I take that integral when t goes from minus infinity to plus infinity of any function f of t times delta of t minus capital T delta dt, I get f of capital T. What is it that I'm doing here? Let me just show you graphically. This is t. This is my function f of t, or signal f of t. I should always say signal. I just keep on saying function, but function of time is a signal in our definition here. Here's the point t. This delta is delayed for t, so here's our delta here. So what am I doing? I'm taking the delta of t minus capital T, multiplying with f of t, and looking for the area under the curve. And what shifting property claims is that the area under the curve is exactly the value of the function at f of t, at this capital T. So let's prove that this is the case. So I have an integral when t goes from minus infinity to plus infinity, f of t, delta of t minus capital T dt. Now I can say that this is an integral when t goes from capital T minus to capital T plus, f of t times delta of t minus capital T dt. Why is it that I can say that? Well, according to the first property that I have for delta, delta is equal to 0 everywhere except that point for which the argument becomes 0. Here the argument of delta becomes 0 when t is equal to capital T, right? So everywhere else outside of this point, I'm multiplying f of t with the 0. Therefore, the area under the curve is equal to 0. So instead of this integral boundaries from minus infinity to plus infinity, I can only integrate within an immediate vicinity of this point, capital T. Now, since f of t is continuous function, and this interval is tiny, right? It's infinitesimally small, then f of t is really a constant over that interval, right? Because it's essentially only one point. So the value of f of t across this entire small interval is f of capital T, right? It's such a small interval so that the function doesn't change. So since it's constant, I can take it outside, and this becomes f of capital T integral when t goes from t minus to t plus delta of t minus capital T dt. Now this is the area under the curve of a delta pulse. What is that area?
1.
1. So this whole thing is 1. So the value is f of t. So that's an interesting property. We're going to use it quite a bit throughout the course. So just, I guess, let me rewrite it again, using shifting property. One may write f of t is a sum when tau goes from minus infinity to plus infinity, f of tau delta of t minus tau d tau. Okay. So that's an interesting equation that we're going to utilize later. Also, I can say that this is tau goes from minus infinity to plus infinity, f of t minus tau times delta of tau d tau. So all of these are valid, because you can see this one is essentially only exists when tau is equal to t, and then that's f of t. And the same here only exists when tau is equal to 0, which is f of t again. So I can, these two integrals are kind of origin of the convolution that we're going to introduce a little bit later. So that's the second function that is of high importance to us, delta function. Remember this definition. It will, all three parts are important. You cannot just say, oh, you drop any one of them and get consistent results. It is 0 everywhere except 0. It's infinite at 0. And its area under the curve is equal to 1. The third function that is going to appear a lot is exponential. Right? So let me just, I know it's a little bit trivial, because I know you've seen it many times, but let's review the part that are of immediate interest to us here. So exponential function. So f of t is going to be e to the st, right? In this course, this s is a complex number, and it consists of real part plus j omega, where omega is imaginary part. So s is a complex number. We call it complex frequency for the reasons that I'm going to explain later. And exponential function operates on this complex frequency times the t. Now, this is a compact way of writing it. I can expand this a little bit and use that as an opportunity to remind you of some important identities that we use all the time. So substituting this complex number inside, I get this, and then I can split this into two parts. I can split the real and imaginary part. So this becomes e to the sigma t, and then times e to the j omega t. And one more rewrite. I can write this as e to the sigma t, and then cosine omega t plus j sine omega t. Okay? So to write this equation here, I have used Euler's identity. Which is, I hope, a good friend of yours. You've seen it many times. They like when you see it. So e to the jx is equal to cosine of x plus j sine x. Okay? So that's one of the identities that is going to appear all the time. Now, I'm sure you've probably seen this, but this is a good way for me to refresh. You know, a lot of students tend to memorize this and wonder where it's coming from. And I always thought that the best way to remember something is to understand where it's coming from, right? The first thing that leads to understanding where this is coming from is understanding what this is. What is e to the x? How do we define it, right? And if somebody asks you, what is e to the x? What would be the answer? What is the only correct answer? Yeah, exponential, but
Space.
Huh?
This Taylor series.
Space.
Yeah, there you go. The only you gotta think about it. If you are human, we only know to do 4 things. We need to add, subtract, divide, and multiply, right? If you're a computer, you're even dumber. All you know how to do is add and take a complement, right? So everything else needs to be defined in terms of these operations. So when you think about what is the proper way to define e to the x, right? It is this: e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on, right? So this is, I mean, there are some powers here, but these are trivial. This is x times x, x times x times x, right? So I know how to compute e to the x here, right? And this is the definition of e to the x. The stuff that we attach later, you know, this is, exponential and stuff, this is all kind of descriptions that we tend to memorize. But this is the definition. This is the only proper way to define any function in terms of the 4 elementary operations which lead you to Taylor series. In this case, Maclaurin series, right? Because it's about priority. Now, the second thing that leads to this one, well, let's substitute e to the jx in here. So what is the definition of e to the jx? Well, it's exactly this if when instead of x I put jx. So if I plug this, this becomes 1 plus jx plus jx squared over 2 factorial plus jx cubed over 3 factorial plus so on. Now we carry on this here. Let's separate real and imaginary part. I have real 1. Jx squared is what? Minus x squared over 2, right? Then the term here is going to be jx to the power of 4 over 4 factorial. So j to the power of 4 plus 1, right? So it's going to be x to the 4 divided by 4 factorial. So plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial and so on, right? So that's my real part. Then let's look at imaginary part, plus j. Then what do I have here? I have x. Then from here, j cubed is minus 1. So I have minus x cubed over 3 factorial plus x to the 5 over 5 factorial and so on.
So excuse me, jx squared is supposed to be plus.
J times j is minus 1. J is square root of minus 1. So square root of -1 squared is -1, right? So this here is the real part, this is the imaginary part. Guess what this is? What is this? Cosine. This is cosine. What is this? Sine. So we get that e to the jx is cosine of x plus j sine of x. Right? So when they ask you what is cosine, right? It is not ratio of two, sides of the triangle, right? Because we can say cosine of 35 million and know how to evaluate it. The cosine is this, sine is this, right? It happens that the ratio of the opposite side over the longest side is a cosine, but that's not the proper definition of the cosine. Definition of the cosine is this. And then if you look at definition of the e to the x and you plug in jx, it happens that this is cosine x plus j sine x. Now, once you know this, then you can do something like this. E to the minus jx is cosine of x minus j sine of x, right? Because you can plug in minus x in this equation. Cosine is an e. Cosine of minus x is the same as the cosine of x. Sine of minus x is minus sine of x. Now, if I add these two, I can actually get cosine of x as e to the jx minus e plus e to the minus jx over 2. And I can do the same thing if I subtract these two. So I get sine of x is e to the j of x minus e to the minus jx over 2. So we're going to be using all the time this one and these two, right? You've seen how they come to be, where they're coming from, and it would benefit you greatly to just know them. And most of the students know them, except that I made a mistake, right? 2j. There's a j downstairs. Okay. All right. So these are the three functions that I want to highlight right now. It turns out we're going to be able to express pretty much everything using these three functions, right? In this course, at least. Let's continue and define something that is called symmetry. So even and odd functions. There is a first definition. F of t is an even function if f of t is equal to f of minus t. Right? That function we call even. Now, why did I call this a symmetry property? Because this function, if the function is even, it exhibits the symmetry about the y-axis. So if this is t and this is f of t, even function might look somewhat like this, right? You can think of this as a mirror. Whatever is on one side of the mirror is on the other side of the mirror as well. In other words, if I locate a point here, and I go to the other side, there's a point sitting on the other side with exactly the same value.
Is it symmetric? The symmetric functions is the same thing?
Well, there are different ways of having a symmetry. This is even symmetry, right? We will see there's odd symmetry, there's even symmetry, right? So the symmetry around y-axis is an even symmetry. If I take this function, take scissors and cut it here and flip it on the other side, it would fall on the top of itself. Now, there are some examples, so let me give you examples of even function. Let's say f of t is equal to constant. that's an even function, right? It's across the entire axis, it has the same value, right? So that's a trivial even function. F of t equal to 2t squared. That's an even function, right? F of t equal to cosine 2 pi f t plus t to the 4 is an even function and so on. Just look, you can see what we're looking for. We're looking for the function when I plug in minus t here, I get the same value as when I plug in t. So if I go this way or this way, I get the same value. So that's the first type of symmetry that we're going to define. Then f of t is called odd function, or it has odd symmetry if f of t is equal to minus f of minus t. These functions have also symmetry, but the symmetry is not about the y-axis, it's about the origin, right, of the coordinate system. So this is f of t. If the function looks like this on this side, then it will look like this on this side. So here, if you locate a point on one side and you draw a line through the origin, there will be a point on the other side with exactly the opposite value that belongs to this function. Example of odd functions. Like f of t equals 3t minus 2t cubed. That's an odd function. You can try it. Substitute, let's say, try. F of minus t, in this case, becomes minus 3t minus 2 minus t cubed. And you can see that this is minus 3t plus 2t cubed, or minus 3t minus 2t cubed, right? Which is equal to minus f of t, right? So f of minus t is minus f of t. This is an odd function. Another example would be f of t is equal sine of 2 pi ft plus arctangent of 3t, right? Both sine and arctangent are odd functions. So that's how we define it. There are some rules that help you. First, or some observations that kind of come along with all of these definitions. So the first note is f of t may be even, odd, or neither. You know, last time when we talked about signals, we said it's either power or energy. There's no third alternative. Here, majority of functions are neither, right? Majority of functions don't have the symmetry. Symmetry is a special property that some of them may possess. The most famous example, and I want to do it here because every time I say it, and every time in exams, for some reason, students forget about it, so let me put it here. The example of the function that has neither odd nor even symmetry is this function, e to the jx, right? For some reason, students think this has even symmetry. I've seen that in many problems, especially when it's dangerous, like in exams, right? That they assume even symmetry of this. Whereas we already know e to the jx is cosine of x plus j sine x. So this function has an even part and odd part. But as a whole, it doesn't have a symmetry. It doesn't have either one of these symmetries, right? So that's the first observation that I want you to remember. The second one is that if you have odd function, and you multiply odd function, what do you get? Even function, right? If you had odd and you multiply even, what do you get? Odd. And if you have even and you multiply even, you get even. So they kind of behave like a plus minus, right? Where odd is minus and even is plus, right? Because you have odd times odd, minus times minus is plus, and so on, right? So that's another important observation. And note 3, we would frequently get a task of integrating the function. If the function has some sort of symmetry, our integration becomes a little bit easier. So if f of t is odd, then if I integrate in symmetrical borders f of t dt about the origin, what is the result that I get? If I'm integrating odd function in the symmetrical borders, what do I get? No, 0. Okay, so that's a very good that somebody mentioned 2 times. Let's look at this. Is an odd function, right? F of t, and it's odd. So here's what I'm doing. I'm having a symmetrical borders, and then I'm integrating in the symmetrical borders. You see that whatever I accumulate on one side, I cancel with the other side, because f of t is minus f of minus t, right? So the integral of the odd function in symmetrical borders is equal to 0. And this will help us tremendously, right? Because a lot of times integrals are going to be really complicated, and if you identify symmetry, you just set the result. You know, if you don't identify symmetry and you start computing, chances are you're going to make a mistake, right? So always look for symmetry. Symmetry is always a good friend of ours. Now the second subnote here, if f of t is even, then integral from minus t to t, f of t dt, can be seen as 2 times an integral from 0 to t, f of t dt. Right, in this case, you know, if you have an even function, and let's say this guy looks somewhat like this, then you can see that whatever I have on the left-hand side is the same what I have on the right-hand side. So this entire area is equal to this times 2, right? So you, instead of integrating from minus t to t, so this is minus t to t. I here, instead of integrating from minus t to t, I integrate only from 0 to t and multiply by twice. These are all self-explanatory, you know, and easy things. The problems we have is there are a lot of them, right? So, and they all kind of appear all the time. So, you know, reviewing them is always beneficial, right? Now, the maybe novel thing that you're not familiar is that every function can be decomposed into an even part and odd part, right? So let's say the function has even symmetry, then it's trivial. Odd part is equal to 0, and even part is the function itself. If the function has odd symmetry, then even part is 0, and the odd part is the function itself. But if the function is in this neither category, then I can create its odd part and its even part, and the sum of these 2 parts is going to be function itself. So let's first formally show that that's the case, and then I'll give you an example to illustrate how we actually do that. So if the function is neither odd nor even, it can be shown that that the function can be represented as sum of 2 parts. One is going to be even part, and the other one is going to be odd part. So how do I put it here? So every signal or every function may be represented as a sum of its So let's take x of t. It may not have any kind of symmetry. Then I can say that this is 1/2 of x of t plus x of minus t plus 1/2 of x of t minus x of minus t. So I create this, I kind of separate this way. You can see that left-hand side is equal to the right-hand side because this x of minus t is going to cancel with this minus x of minus t, and then x of t and x of t will add half of x of t from here, and with this give me x of t. But this part here is even, and let me call it x even of t, and this part here is odd, x odd of t. Right? So let me illustrate this through an example. Consider a function f of t is equal to e to the minus at times u of t for every t, right? So it's a product of exponential and this step function. How does this one look like? Well, here's our coordinate system. E of t looks like this, right? It goes to, this is e to the minus at. It goes to 1 and then kind of quickly goes towards 0. U of t, we know that this one looks like this. Right? So the product of these two is 0 before 0, then it jumps to 1, and then it decays like exponential. So this is our function, that this solid one is f of t. Does it have symmetry? Any kind of symmetry? No, it's neither odd nor even. But let's look what happens when I look at this, when I form this and when I form the other thing. Let's see how those functions look like. So let me say something like this. F e of t becomes 1/2 f of t plus 1/2 f of minus t. So in our case, this becomes 1/2 e to the minus at times u of t plus 1/2 e to the at times u of minus t, right? And how does this function look like? Well, let's draw it. Let's draw this first part. This first part, we're kind of basically, what we have here is just scaled by 1/2, right? It's 1/2 of f of t. So if I call this 1/2, then this is how the first part looks like. So this is, this part here is 1/2 of f of t, right? How about the other guy? The other guy is exponential that is increasing, right? E to the at. For t equals 0, it goes to 1/2, right? So the other guy starts by looking like this, right? Now, u of minus t, how does u of minus t look like? Well, u is equal to 0 whenever t is negative. So when t is positive, u of minus t is equal to 0, right? So this is u of minus t. It is equal to 0 for all positive t's, and then it is equal to 1 for all negative t's, right? Because the negative t makes minus t positive, so this one turns to the left, turns on to the left. So now multiply this and this. What do you end up with? You end up with this part, right? Only this part. So this is this function here, f e of t. Now tell me, is this an even function? right? It is, right?
Yes, yes, ma'am.
It is e to the minus at to the right and e to the at to the left, right? So that's an even part. If I did the same kind of analysis for the odd part, here's what I'll get. So f odd of t becomes 1/2 f of t minus 1/2 f of minus t. So we kind of already know how to draw this. 1/2 f of t looks like this. So this is 1/2 f of t. It goes here through 1/2. Now, f of minus 1/2 f of minus t, this is f of minus t. But minus 1/2 of f of minus t flips this down, right, below y, below x-axis. So you end up with this, where this is minus 1/2. So this is 1/2 f of minus t with minus up front. Now tell me, what kind of symmetry does this one have? Odd symmetry. So you've seen now we took a function here that is not symmetrical, doesn't have neither symmetry, and we decompose it into this one, which has an even symmetry, and this one that has odd symmetry. Now add these two. What happens? To the right, you have 1/2 f of t and 1/2 f of t, so they will add up to be f of t. And then to the left, these two will cancel. So it will actually give us back our function. So that's a kind of proof and illustration. We're going to use that a lot to simplify some integration and some analysis in the future. Just be aware that every function can be decomposed as it's even and its odd part. At this point, I'm going to stop talking about signals for a moment. We have enough. Remember, these couple of lectures up front are kind of review lectures. I'm sure you've seen all of these somewhere, but it might be at disjoint places, so we kind of put it together in this one course so that you have it all in one spot. The second thing that we need to define, and that's going to be major object of our study, is a system. Right? So what is a system? And I'm going to kind of write the definition. There are various ways of defining it, and they're kind of guided by what is it that you're actually trying to do. And in this course, we define a system in the following way. A system is an entity that processes a set of signals that we refer to as inputs and produces another set of signals that we call outputs. As I said, this is one way of defining it. It's kind of instructive from how we defined it here, because it kind of tells us about what this course is all about, right? You can define systems in many different ways, and I'm sure it's defined in some other classes, and a lot of times they say it's a collection of blocks or whatever. Here, we have this particular approach where we look at the box that we call a system, and we define this system through its input-output relationship. We assume that this system is excited by a set of signals, x2 of t, xn of t, and we assume that the system will react to these inputs and produce a whole bunch of outputs, which are, again, another set of signals. So what does the system do? It performs a mapping between input set of signals and the output set of signals. The theory that we're gonna uncover in this course will allow us to do three things. So linear system theory, right? So let me just continue here. So I don't think I need to. I just may mention. I don't need to build a big case why this is useful, right? You can think of many examples where you have a box that you feed some signals at the input and you get some signals at the output. What the system theory does is three things. Allows. First thing, description of the system. And again, we're looking at particular description that's of interest to us. You know, if you look at this white, what is this, extension cord, and I treat that as a system. When I say description, I don't mean white, right? Or I don't mean half a pound, right? What I mean, there is an input signal that is coming into this, and there are output signals that are coming out of there. So I want to describe this system with a set of equations that allow me to map the inputs to the outputs. So I'm abstracting the system. I'm really, from the system theory standpoint, I'm not really interested in the system, you know, as a physical entity. I'm interested in a model of the system that allows me to map its inputs into the outputs, right? So that's the first task. We need to describe systems. And you will see that, you know, like everything else in this world, it's going to be described through some sort of differential equations, right? Because our world is guided by differential equations for the most part, until you get really subatomic and really small. So description of the system, that's the first thing. The second thing that now that we have described the system, then calculations of the outputs given set of inputs. So we want to be able to calculate what the system is going to do, the prediction of the system behavior. So let me put that way, prediction of the system behavior. And this is essentially calculation of outputs for a given set of inputs. And then the third thing that we want to be able is to do. Now this is where we have description. This is essentially analysis, right? Analysis task. Giving you, here are the inputs, here's the system, what comes at the output. Now, the last and most sophisticated task is, here are the inputs that I get. Here are desired outputs. How does my system look like? And this is a design task, right? I want a linear system theory in general, and linear system in particular, allows us to do a design, right? In essence, devise a system or devise model for a system that will turn a certain set of inputs into a desired set of outputs. So allows us to design a system that maps inputs into desired set of outputs. We are all electrical engineering background, so these are all familiar to us. Description of the system is our circuit, right? I draw a circuit. This is a model of the system. I put a symbol for a resistor. It may be a resistor, maybe a wire, maybe whatever physical entity, but I take this circuit and abstract it as a circuit model. So that's a description of the system. Analysis is I'm able to predict every voltage and the current, powers, whatever I want to predict in this particular circuit. And the last thing is I want to design a low-pass filter that has these characteristics. How does this filter look like in terms of equations, and then later on we make it a physical reality. Now, we're dealing with different kinds of systems, and again, from the standpoint of how do they map inputs into the outputs. And we have, I'm going to kind of list some systems here. We're going to define some of these in more detail. Obviously, we're not going to tackle all possible systems. It's beyond the scope of this course alone. Actually, the course says we're going to tackle only linear systems. And in system theory, that's the most, I would say, elegant theory and kind of the easiest one. And you will see that as soon as you kind of venture out of it, the problems become pretty difficult very fast. So let's take a look at classification of the systems. Similar how we look at the different ways of classifying signals. First classification is linear versus nonlinear. The second classification is constant parameters time varying. The third classification is memoryless or with memory. The fourth classification is causal, non-causal. The fifth one I have here is continuous time, discrete time. Analog digital. Invertible, non-invertible. Stable, unstable. Deterministic, probabilistic. Okay, all of these are different categories. I want to have them in one place, then we kind of go and talk a little bit more about each individual one. A lot of these, some of them we're covering like linear, constant parameters, memoryless, causal, all of these we're going to, both continuous and discrete, we're going to cover in this course. There are other courses that deal with, for example, linear time varying systems. Some of you have attended this kind of courses. Can you think of a linear time varying system? How about adaptive filter, right? That's a linear time varying system because it adjusts its parameters over time based on whatever is being processed as your signal, right? And so on. So let's first discuss the classification linear versus nonlinear. Linear, nonlinear. Now, there are again different ways how we can define this. Since we haven't really talked about differential equations, one of the easiest way of defining whether the system is linear or nonlinear we say that linear systems are the ones for which the superposition holds. That's equivalent to being a linear system. So linear systems for which superposition holds. Now, what is a superposition? Let's take a look at the system here. Let's call it an S. And this is the system behavior. If I present an input x of t, I get output y of t. Okay? So if x of t or x1 of t is mapped by this system into signal y1 of t, and x2 of t is mapped by this system into a signal y2 of t, the system is linear, and I should say a x1 of t plus b x2 of t is mapped into a y1 of t plus b y2 of t. The system is linear. You know, if you don't want to use math, the way how you would say this is you would say the system that's presented with a weighted sum of the inputs produces the weighted sum of the corresponding outputs. Right? So, in other words, there's no mixing here there's no product between the inputs. Whatever comes as a sum comes as a sum in the output of individual responses. So this system, to calculate the output to the sum, I can really forget about this one. Calculate first the output to the first, calculate the output to the second, and I sum the outputs to get the output to the sum of the inputs. Now, let's let me put some notes. First note, in practical applications, there are very few systems that are truly linear. For all sets of inputs, for the entire range of inputs, right? Or possible set of inputs, right? So, you know, let's take a look at an example. Let's say this S is a linear amplifier, right? So you take sum of the two signals, you get the sum of two of them amplified. But this is only holding for a certain range of input signals. If one of them becomes too powerful, then the amplifier gets out of its range. And that's the case with a lot of systems. Linearity is something that in a lot of applications we actually design for. That's a goal. And we are set to design our system, but one of the major inputs is going to be, okay, I want it to be linear, but over what range? And then we make sure it's linear over this range, and then you add additional design constraints to make sure that what is presented to the system never goes out of this range. Naturally, most systems are non-linear, right? So this property is kind of novel property. It doesn't occur on its own. It has to be really either designed for or naturally occurs over a certain range of input values. Another note, and this is also kind of one way of defining linear systems is you can say linear systems are described by linear differential equations, right? Or difference equations. So linear systems are described using linear differential or difference equations. That's actually one way how you can define it, and then if that's the case, it's easy to show that the superposition holds, right? Because linear differential equations or difference equations, kind of from the linearity of these equations, the superposition is derived. So let me look at an example and kind of show what does this mean and how you actually demonstrate linearity of a particular system.
New message from the habit.
So let's take a look at an example. Consider a system that's described with the following differential equation. Delta y of t over dt plus 3 y of t is equal to x of t. This is a linear differential equation of the first order with constant coefficients. Right? So all that we have already seen. Y of t is output, x of t is input, so this is a non-homogeneous because it has an input that's different than 0. So, so I feed x of t in the system, and what comes out is y of t that's described with this differential equation. So let's say x1 of t produces y1 of t, and x2 of t produces y2 of t. Let me form an input x of t, which is k1 x1 of t plus k2 x2 of t. And let me feed that into here and see if I can demonstrate that the superposition holds. So from this first equation, x1 of t producing y1 of t, I can write this dy1 of t over dt plus 3 y1 of t is equal to x1 of t. This is the same statement as this one, right? The x1 of t, y1 of t pair satisfies this differential equation that describes the system. Along the same lines, dy2 of t over dt plus 3 y2 of t has to be equal to x2 of t. And that statement is essentially saying that system performs a mapping between x2 of t and y2 of t. Now, if I sum these two equations, do weighted sum, multiply this one by k1, and multiply this one by k2, and then sum these two equations, here's what you get. D over dt, k y1 of t plus k y2 of t plus 3 k1 of times y, k1 times y1 of t plus k2 times y2 of t is equal to k1 x1 of t plus k2 x2 of t. Now if you zoom out, you can see that this here is your x of t, and this x of t is mapped into this function, whatever this function is. Let me call this y of t. Right? Because the system satisfied this equation, d over dt, y of t plus 3 y of t has to be x of t. But now if you look at y of t, it is k1 times y1 of t plus k2 times y2 of t. So if my input is weighted sum of the individual inputs, My output is weighted sum of the individual outputs. Where is the origin of this? It's the behavior of the equations, differential equations. They are linear differential equations. So linear derivation is a linear operator, and these are linear differential equations, so that's where the superposition came from. Okay, so let me give you a list of suggested problems. Let me just remind you what this means. These problems are the ones that exercise the material that I cover in every particular lecture. There's going to be a lot of them. Your midterm and exam is going to be from these problems. So what I do is I just put them all in a head, and then I take a few out, and this becomes your midterm and finals. So just do them, right? That benefits you greatly. But okay, so suggested problems. 1, 4, 1, 1, 4, 3, 1, 4, 4, 1, 4, 6, 1, 4, 10, 1, 5, 1, 1, 5, 3, 1, 5, 6, 1, 5, 8, 1, 5, 11, and 1, 5, 12. Now let me just make a final comment here. A lot of you have international edition of the book. The numbers I gave you here relate to American, US edition of the book. The international and American editions are identical, but the numbering of the problems are different. On the website, you're going to find I've copied the problems from American edition. So even if you don't have the book still, you can go there and find these problems, right? But if you have a book that's international edition, compare and then just do the mapping, right? And find also a friend who has American, so that every time I assign the problems, you can determine what the mapping is. Because they are really the same problems, but they're in different order, and that makes it a little bit different. Okay? That's it for today.